Hello, welcome once again to this final in a series of lectures on discrete time signal processing. Now this series of lectures we've covered starting from extracting a discrete time signal from a continuous time signal, the various characteristics of the discrete time signal and its applications to systems, discrete time systems, and the properties of discrete time systems. And now we understand how, if you give a discrete time signal to a discrete time system, what would be the response of such a system to a discrete time input signal x of n. So first, let's have a block diagram. You have a discrete time input signal xn. You have h of n. Now this h of n is the response of the system to delta n. And delta n is the impulse response. Delta n is the impulse, and therefore h of n is called as the impulse response of the system. So basically delta n is a small disturbance that you give approximately at say n equal to 0, and you observe what happens to this, and the system gives some response, and that response is called as h of n. Now to this input signal, having an impulse response hn, what happens to the output yn of the signal? Now yn is given by x of n convolved with h of n. This property of x of n and h of n is called as the property of convolution between the input time signal and the impulse response of the signal. Now basically this convolution operator is basically multiplying, shifting, adding, correct? So you have x of k multiplied with the shifted versions of the impulse response, or vice versa, because convolution is a commutative property. X of n convolved with h of n is similar to h of n convolved with x of n, and therefore you get x of k multiplied with shifted versions of h, and then this shifting is done from minus infinity to plus infinity. Okay, now why does this output yn be a convolution? That is what we'll be discussing in this presentation. Let's go to the next slide. Now before we actually go to what convolution is, we have to understand two things. First is a signal decomposition. Every signal xn can be decomposed into its components. Each component can be in terms of an impulse. For example, x of n, say it's from n equals to between -1 and n equals to 2. Now I can write this x of -1 here as x of -1 in magnitude with delta of n plus 1, because delta l plus 1 will be existing only at n equals to -1. So that it's a shifted, it's an advanced version of the impulse function, and therefore it's 1 into delta n plus 1. Similarly, for x of 0, I can write it as 3 times delta n. Same for x of 1 and x of 2. So basically x of n, the input signal, is additive version of all these decomposed parts. So my next slide will be the decomposition given in xn equal to x of -1 into delta n plus 1 plus x of 0 delta n plus x of 1, and so on. This equation can therefore be summarized as x of k multiplied with shifted versions of delta. If you see, delta is shifting here from -1, k is shifting here from -1 to +2. So this shift can occur all across from minus infinity to plus infinity. So this is another way where the discrete time input signal can be represented. X of n is equal to summation from minus infinity to plus infinity, x of k into delta of n minus k. Now the second thing which we require to understand is discrete time system, delta n, if you give it the input, you get an impulse response h of n. However, that's the reason we studied the characteristics of discrete time systems. And one of the characteristics was time invariance. So time invariance systems, if you give delta n minus k as the input, you get the impulse response shifted. That's what we've written there. The time invariance systems, the response for time shifter impulse function is also shifted by the same amount of time. But remember, this occurs for time invariant systems only. Then for linear systems, if I give a scaled input signal, or if I get a scaled delta function, my output also is going to be scaled by that particular amount. So let's have a discrete time system. You have delta n multiplied by n, so the impulse response hn is also going to be shifted by the same amount. So how this shifting and scaling is done in case of linear time invariant systems. Therefore, when we study discrete time signals, we generally study LTI systems, linear time invariant systems. Okay, because only for linear time invariant systems we can have the impulse response shifted and scaled by the same amount as the impulse function is done. And remember, the impulse function is also a part of the input signal xn. So if you are dealing with delta n, that means we're dealing directly with xn also. Let's go to the next slide. Once we've considered this LTI systems, for time invariant, this is a concluding part of this thing. For time invariant system, the response of the time and shifted impulse function is also shifted at the same amount of time. The system is linear. Scaled input causes an identical scaling in the output signal as well. Next. And that's what we've done. X of n, suppose, is a delta plus 1 plus b delta n plus c delta n minus 1 plus d delta n minus 2. Its output is, if xn is in terms of delta, output is, remember, output is a into h of n plus 1, b h of n. The output is also scaled or shifted by a similar amount of time. So this is what we've shown here in the graph. For the linear time invariant system, if you give a delta n plus 1, b into delta, this is b delta n, c delta n minus 1, d delta n minus 2, the output will be a into hn plus 1, bhn, chn minus 1, and dh of n minus 2. Okay. Now, therefore, combining the impulse response property, okay, that delta n minus k is the shifted version and scaled will give us mk and h of n minus k, and also combining the signal decomposition property. You have the signal decomposition property x of n in terms of delta, and delta gives response of h. So if you're combining this and these two together, you say that your output response y of n will be nothing but the convolution of x of k with h of n minus k, because your yn is nothing but dependent on, let's go to the back slide here, yn is the output of a linear time invariant system. It depends upon xn depends upon delta n, and delta n depends upon h of n minus k. So you're combining these two properties to get y of n as summation of x of k and shifted versions of h of n minus k. In convolution, this is also called as convolution operation. So in convolution, we need to know about the impulse response of the system h of n to get the output y of n. Thank you so much.